All right, thank you. Does this work yet? No? All right, I'll just talk real loud. Can everyone hear me? Cool. All right. All right, let me get a little closer so I can. All right. So the title of this work is Evaluating Fuzz Testing. It's work done with George Cleese, myself, and Benji, and Mike Hicks, University of Maryland, and Shi Wei at the University of Texas at Dallas. So we're here today to talk about evaluating fuzz testing. There are many new fuzzing papers and new tools that come out. But how do we know that these new papers and new tools represent an advance? These papers are presented with an empirical evaluation that the tools or the techniques find more or cooler bugs than prior tools, so that's our metric of progress. These evaluations are the evidence of advancement of the state of the art. Our question is, are those evaluations themselves reliable? So in our work, we looked at a survey of 32 recent fuzzing papers. Surprisingly, we found that no paper followed what we feel are best scientific practices for an empirical evaluation. So we conducted our own experiments to see if we could find evidence that not following these practices could lead you astray. Surprisingly, or unsurprisingly, we found that yes, those practices do exist for a reason. So now let's talk about briefly what fuzzing is, and then later what our study of fuzzing evaluation found. So fuzzing is a kind of random testing. It performs repetitive concrete evaluations of a program with mutations applied to the input for each execution. It watches for that program going wrong in some way, crashing or hanging or throwing an exception, or some sort of evidence that there might be conditions for a vulnerability inside of the program. This is a very successful technique in industry and academia. It finds lots of bugs. It's very easy to scale. It's pretty easy to interpret the results and the output from it. Lots of mature tools exist that you can start using immediately. So that's cool. At its core, fuzzing is an iterative process. It builds up starting from an initial corpus of seed files. We choose and mutate elements from that corpus, keeping mutations that produce interesting behavior, where interesting is a sort of parameter to the system overall. Eventually, after some done condition is met, which itself is another parameter, which perhaps is finding a crash at all in one fuzzer, or running out of a fixed time bound that you have available to you, this process stops and we're sort of left with whatever inputs and observations we have at the end. So we can characterize all the fuzzing papers we evaluated inside of this general framework, and probably all fuzzers can fit inside of this framework. So to evaluate your fuzzer empirically, you need to have some key ingredients. You have a baseline to compare yourself against, different benchmark programs to fuzz with both your fuzzer and the baseline, and a measurement of progress, the number of crashes that you find, the number of true bugs that you find inside of your benchmark programs, increasing in coverage between your program and baseline across the test cases you generate, and so on. You also need to explicitly identify and control for configuration parameters, such as what seed file or corpus of seed files do I start with, what is the timeout for the system overall when I'm evaluating it, and then a sufficient number of independent trials that compare your configuration against the baseline. So when we looked at our survey, we found that no paper did all of these things, but some did come close. And there's a detailed table with a breakdown in the paper that you can look at. So we ran our own experiments over the summer using AFL as a baseline and AFL Fast, a variant of AFL that appeared at CCS in 2016, as a hypothetical research tool. We chose AFL Fast because it was available, the code was there, it was easy to set up. The comparison to our baseline tool seems pretty straightforward. And so then based on what we saw in these experiments that we ran, we'd like to give the following advice to scientists that are doing fuzzing research. So bottom line up front, do these things. Run multiple trials and use a statistical test to compare the results across the multiple trials for your base case and your experimental case. You should make your parameters explicit in your evaluation. Use a longer timeout value for a particular trial overall wherever possible, and more time seems to be better. You should use a diverse set of programs for your benchmark programs when you're evaluating your fuzzer. You should not use just one trial or simply compare the average of some fixed number of trials. And you should not use stack hashing or coverage as a performance metric to compare your tool to a baseline tool. So now I'm going to delve into some of the parameters we looked at and their evaluations, the papers we looked at and the parameters that they chose for their evaluations. I'll also present some of the experiments we did that show how these evaluation shortcomings can impact results. So we looked at 32 papers across 6 years of research activity from 2012 to 2018. Each paper had different goals, but all tried to improve some sort of core aspect of fuzzing. So we characterized and evaluated each paper across 5 different axes. And those axes are what benchmarks they used, their approach to how many trials and controlling for variance across those trials, the performance metric they used, what treatment of seed file they presented, and their overall timeout for each particular experimental run. So let's look at our recommendations that we gave on the previous slide through the lens of each one of these axes. So first, let's consider performing multiple trials. So of the papers we looked at, 17 didn't say anything about performing multiple trials. 15 said that they did perform multiple trials, but with a varying number from paper to paper. 3 characterized the variance from run to run of those trials, but none of them used a statistical test when comparing between the number of different trials. So this statistical test would characterize our confidence in the effect that the fuzzer has when it runs from the base case to the experimental case, running multiple times. So how does this matter? Well, ask yourself, does a random process have variance? Fuzzing is a sort of inherently random process, and what effect would that variance have on our evaluation? So yes, a random process certainly can have variance. So in these two plots, the x-axis is time, sort of going from when we start our fuzzing process to 24 hours, and then the y-axis are the number of crashes that are found by the fuzzer and judged to be unique by AFL. So then the red and the blue and the green lines, although you can't really see a green line in one of them, but it is in the legend, indicate the cases for the 2 different fuzzers that we're comparing against. So the solid lines are the means, while the dotted lines are confidence intervals, and then the extreme dotted lines represent the minimal and maximal values that are found across all of the runs in both cases. And for these figures, there are 30 runs in a base case and then another 30 runs in the experimental case. So in the right-hand case, it's pretty obvious they're doing about the same. And if you're only looking at the mean, or if you were choosing sort of one or the other at random from one of the 30 trials, you could arrive at a conclusion that the performance of these 2 tools seem to be about the same. However, in the left-hand case, the blue maximum, which is the sort of, it's there, you might have to squint to see it, is sort of intermingled a bunch amongst the means for the red. So if you had a bad or good, depending on your perspective, day in Vegas when you were choosing one of the trials from one case and one of the trials from another case, it could go one way, but then if you made a different choice, it could go a different way. So either way, you could come to drastically different conclusions when you present the impact that your fuzzer has. So next, let's look at the choices for seed files. So fuzzing starts, or can start, lots of documentation recommends it starts, from mutating an existing seed file. So what seed file should you use? So there is some sort of README and folk recommendations for what choice this makes. Do those choices matter? So on reflection, it's not hard to imagine that the performance of fuzzing could change quite a bit based on the seed. The seed is effectively identifying the starting point in a large search space, where each search is a particular concrete execution of the program after mutation. And if it's not considered carefully, it could suggest that algorithmic improvements that don't exist in general actually do exist, where the real parameter in play was your particular choice of seed file. So what did papers do? 30 papers identify the use of some kind of seed file, with 10 providing further information. 9 say they use a seed file that represents a valid input to the program, but concretely, what exactly was that? If I wanted to reproduce it, I need that particular seed file. That choice could matter. 2 papers use an empty seed file, which seems a little counterintuitive. Why would I start from something non-existent and then build up? Well, this process is generative, so through feedback, it will synthesize for itself, and there are some cool blog posts from the AFL author that show this. You can sort of pull out of thin air a valid input file from using coverage only as a feedback metric. So we think that perhaps that represents a good default if you're looking at this big search space in general, and it's also easy to reproduce. Anyone can create an empty file. So what practical effect does this choice for seed file have? Well, again, in these 2 graphs, the x-axis is time, the y-axis is the number of crashing inputs found. Green, red, and blue are different fuzzers. So the left-hand side is fuzzing FFmpeg with a non-empty input file. The right-hand side is with an empty input file. So somewhat interestingly, fuzzing with an empty seed over a 24-hour period produced hundreds of crashing inputs for the fuzzers in both cases. But using a valid non-empty seed file produced many fewer cases. The ticks on the left-hand side graph top out at 20, while on the right-hand side it tops out at 450. So that's just a big difference. So next, let's consider another parameter choice, which is the timeout for your overall experiment. So when we say timeout, we mean how long do you leave a particular run running for? So we call this upper bound the timeout. 10 papers chose a timeout of 24 hours for each run that they would use to compare whether or not they use multiple runs. Among the papers we looked at, timeouts vary dramatically from 5 or 6 hours on a sort of lower end bound to months as an upper bound. I mean, that takes some confidence. Just take your fuzzer and leave it running for 3 months and then come back and see what it produced. The danger with shorter runs is that the trends could reverse over time. And indeed, we saw this in our experiments. So for example, here's a short example. X-axis is time, Y-axis number of crashes, red and blue different cases. Let's say that we stopped fuzzing, right here at about the 4 or 6 hour point. And we would say, well, the red one has found 4 crashes and the blue one has found no crashes, so here we are. But what would happen if we let the experiment run for another 18 hours or so? These trends would reverse, and they would reverse in a meaningful way if we look at the confidence intervals around the means. And that crossover point happened, would have happened just after we stopped our first experiment. So this would change the trends totally based on the amount of time. And maybe, if we let this run for longer, those trends would reverse again and then again. So who's really to say what the upper bound is here? So next, let's consider our choice of benchmark programs. So what programs are fuzzed during your evaluation? We call these benchmark programs. So benchmarks should aim to represent a sufficiently large sample of the population of programs one might fuzz. So that way, experimental results on your benchmark that you present in your evaluation should generalize to the overall population of programs that are actually out there whose security properties we care about and we want to find bugs in them. So of the papers we looked at, 30 used real programs. So these are programs you might find on your desktop or laptop right now. Sometimes as many as 100 different real programs were used, but a median of 7 real programs when we sort of summed it all up. Does this choice give us a fair comparison? Are these programs representative? Sometimes you can have a program like, for example, the binutil suite of programs. It's the case that there are 6 programs which are really just different wrappers around one library. So really you think, I'm fuzzing 6 different programs, but 90% of them are the same. So that could lead you astray. 9 papers use purposefully injected bugs, where those bugs are either injected manually or automatically. 4 of them use challenge programs developed for the DARPA Cyber Grand Challenge program. And then 5 of them use bugs injected automatically via the Lava M tool. Do these injected programs, either where the bug has been injected manually or automatically, have ecologic validity? Do these look like bugs we really care about finding? So we have more discussion on this in our paper, and specifically how fuzzing performance can vary based on what type of program or the program you've chosen to fuzz. So next, let's consider how to assess the success of a fuzzer. So how do you measure the performance of your fuzzer? What's a good fuzzer? Ideally, you would count how many distinct bugs your fuzzer finds, since that's what your fuzzer is ultimately used for. But the ground truth is not known for many programs you choose to benchmark. Indeed, if you knew where all of the bugs were in programs on your laptop, that would be like a pretty good day. That's why we're doing this fuzzing process in the first place. So as an approximation, what can you do? Well, you can maybe count up the number of unique crashing inputs that your fuzzing process discovers. But optimizing for that can be bad. You don't want to overwhelm a software developer with a large number of crashing inputs that all turn out to have the same root cause. They'll get kind of burned out having to go through a whole bunch of them only to find out that there was a lot of duplicative work that they did. So 7 papers that we looked at used AFL's notion of coverage to uniquely identify crashes, while another 7 used a notion of perfect ground truth. And then another 7 used this concept of stack hashes or fuzzy stack hashes. So one question we had was, how effective is either coverage or stack hashes at estimating ground truth? So first I'm going to talk about how we took our particular experiment and derived ground truth from those from the fuzzing campaign that we performed. And then we're going to look at coverage, and then we're going to look at stack hashes. So let's say that we have a pile of about 57,000 crashing inputs we found in CXXFilt. How can we determine the number of root cause bugs that were found? So when we fuzzed, because we were sort of aiming to reproduce the CCS 2016 paper, we fuzzed the version of CXXFilt that they fuzzed then, which at the time that we did our experiments was about 2.5 years old. So there had been a bunch of different development activity, about 3 or 4 major point releases that occurred, and about 800 or 1,000 different commits that had occurred onto the code that we were fuzzing specifically. And some of those fixes were even fixing bugs that were identified by the CCS 2016 paper. So how do we assign some root cause to the crashing inputs that we found? Well, let's take the cross product of all of the different 800 or so patches that have been made to the repository from version 226 to 228, and then all of the 57,000 inputs that we found, and then execute the cross product, about 47 million test cases, and produce a very large matrix that looks something like this, that records, oh, in version 1, this input crashes, and then doesn't crash. Then we can go through and find the pivot points where an input goes from crashing to not crashing, and look at each one of those pivot points individually. So this sort of says, here's the place where the patch was introduced that made this particular input stop crashing. So this isn't guaranteed to work in general. In this case, because of the structure of CXXFilt, we got kind of lucky and this worked, but it did produce about 6 or 7 of these pivot points that we manually inspected, and we were able to break a few of them out additionally manually into more fine-grained representations of a particular bug fix. But looking at 6 or 7 things is far more tractable than looking at 57,000 things. So let's say we take that metric and we take the sort of ultimate output of AFL and AFL fast in our reproduction, and instead of counting the number of unique crashes, so instead of counting the number of unique crashes as determined by AFL, we did count the number of root cause bugs found. So there were 9 total bugs that were found. No individual trial found more than 8, which is kind of interesting already. So in these graphs, each bar is a single 24-hour run of either AFL or AFL fast. The height of the bar is the number of unique root cause crashes found where we determined them via the previous methodology, with AFL on the left and AFL fast on the right. So if it doesn't look like there's that much of a difference between these two, it's because there isn't. If we perform a statistical test on the distribution of the number of bugs that were found in both cases, we come back with not enough confidence to conclude that there's a difference between these two tools. So then we were like, okay, another metric that people use is they use stack hashes or fuzzy stack hashes. So a stack hash is a representation of a fixed number of elements on the call stack from the faulting context, sort of going backwards. Usually the number of contexts is 3 or 5. So we took these 57,000 inputs and we computed stack hashes at all of their crashing contexts, and we've had about 550 unique crashing contexts. So then we made this sort of pseudo confusion matrix where each of our unique bugs is in this column, and then we say, oh, associated with bug A are 9 hashes, associated with bug B are 362 different hashes. So already this is telling you, like, well, in our ground truth, we know we have 9 bugs, but if we asked the stack hasher, it would tell us we had about 500 bugs. So that's already a large blowout. So the matches column on this indicates how many hashes are associated only with this bug, and the false matches column indicates how many hashes are associated with more than one bug. So how sort of lossy is that particular hash at classifying that bug. So how can that happen? So one example, if there isn't enough context to discriminate two crashes, imagine there's some deep call to stir copy. Some of these partitions are large, so the last column are the input counts. So for example, bug B represents 31,000 unique inputs, but bug G only represents 2 inputs. So and if you look at the root cause for bug G, it actually makes sense that bug G represents an actual patch for which there would be very few inputs that you would find it. So let's look at one of the root cause bugs that we found. So this is one of the contexts where the program sort of starts to go wrong. The problem is that this work structure has been deallocated, so it contains some elements that are used by xnuvec that have been deallocated and are invalid, but this size pointer remains valid after the fact. So what the code is expecting is it's expecting, oh, if it's equal to 0, I'll do one thing, but if it's not equal to that, I will use this b-type vec value. In this case, it'll use it after it's been freed, which leads to a vulnerability. So the fix is here. In the excellently named squangle mop-up function, we should set this b-size parameter equal to 0 when we deallocate and set to null this type vector. So this patch is pretty far from the context where there are crashes. Due to input-based non-determinism, there are multiple ways to get to a crashing context. So what that looks like is, this is a graphical illustration of that process. So control passes from 1 to 2. 2 is squangle mop-up, which is where we have this fix. We go back to 1, and then anything could happen after that. We go through either 1 to 3, or 1 to 5, or 1 to 5 and 6, and then 1 to 4. But then after any of these, 7 happens. So now we have different contexts that are all leading, that all start at the same place, 7, and then go back to different places. So if we ask stack hashing, hey, are these the same or different? Stack hashing would say, oh, they're all different. But they all have the same root cause. And frustratingly, that root cause isn't actually anywhere on the call stack at this point anymore. So a different case, one where stack hashing actually does work very well, occurs here. So if success is true, we have this mangled value, which is basically, you can think of a cursor. And if the value in success is non-zero, we access it. But if it's like an invalid cursor at this point, we crash. So why is that? Well, if we look at the fix, what happens is that this consumed count function takes in the cursor and mutates it. Consume count tries to advance through the buffer and essentially do A to I. And if it fails, due to like running off the end of the buffer, it will leave the cursor pointing off the end of the buffer and return -1. So the fix is to check for this return value to -1 and then set success equal to 0, which is what was added. So when you look at the control flow for this, it's much simpler. We start at 1, we go to 2, which is the case where the check was added, and then we immediately go, the only thing we can do after that point is go to 3, where the failure occurs. So when we asked stack hashes to localize this, it said, oh yeah, these 500 or so inputs that trigger this behavior, they're all the same. So in more detail in the paper, we cover seed selections, timeouts, the choice for a statistical test, our rationale for that, and multiple trials in more detail. There are also more graphs. To sum up, you should use multiple trials and a statistical test with explicit parameter choices made for seed files, longer timeouts, and a good choice of programs for your benchmark. On that subject, we think there's future work here. So what is a representative fuzzing benchmark? What programs do we care about, like finding bugs in and making our fuzzers better at? Can we build up a ground truth corpus from the history of open source projects like what we did? Is that a valid technique to work from in general? Are there problems? There are some problems that we know about already, but maybe we could have it work for specific programs that have ecological validity. Thank you.
All right, questions?
So I'm really glad you're doing this work. In my experience playing with fuzzers, it makes a big difference whether you seed the thing with a dictionary that matches the. So you didn't mention that issue.
No, I mean there are a bunch of other parameters. That's true. I think you could maybe fold that under etc. If at some point I say there are additional parameters that you should look at, but that's a very good point, and it does matter a lot. Yes. No, it doesn't work. Just yell.
Makes me feel more comfortable. Anyways, I'm Jan Trustworthy from ASU. Awesome work. I think this is super important, especially in our field. It still seems that you're thinking, I mean, your core idea is the most important thing is that high level, how many bugs did you find, and et cetera, right? And then,
Yeah.
what do you think about some possibility for testing? And I haven't had a chance to really think this all the way through, as most things, but testing like each specific part of the fuzzing process. You have that general algorithm, right? And you could have some sort of a fundamentally sound or whatever way to test each specific.
Yeah.
There.
So, sorry, is that?
Before you put it all together and just test the big thing.
I think I've seen in somewhat different projects I've worked on where I'm like, oh, I'm going to optimize this one thing, I'm going to optimize this one thing, and then I'm going to put them together. And for mysterious reasons that takes a lot of time to unpack later on, it actually gets worse when you make two little components. So like one of the papers that we looked at, their contribution was, oh, well, we made it faster to do test case throughput. And it's sort of like, well, okay, it seems like it's fairly intuitive that always doing more test cases is better. I don't know what you're really going to lose by ever doing that. So that seems sound. But what if there's some counterintuitive way where that's not true, and you would only know if you did some kind of end-to-end evaluation?
I'm not arguing against an end-to-end evaluation.
Yeah,
that might be another kind of route.
Right. Yeah. Well, I mean, so then if you have something where you say, well, there are maybe other reasons for I'm going to run the same program over and over and over again. So there's something I can do to make that specific use case faster. That could also have generality outside of fuzzing. So then that could be the total of your evaluation. You're just like, it works. But like for mutator, or like you could maybe say, oh, I'm going to do an independent evaluation only of mutators. And you're like, well, there's probably only one context that you're ever going to use those. So does it really okay, maybe your mutator is cool, but does it help with the end goal? The way to do that is via an end-to-end evaluation. That's I think, and also sometimes there's like so another paper, they sort of did this where their evaluation metric was increase in coverage. So they sort of had this end-to-end evaluation, but they didn't count the number of bugs they found. They said, oh, if compared to the base case, we can generate test cases that have more coverage than the base case. That's good. But there's an implicit, I think maybe they made it explicit, hypothesis in there, which is doing more coverage is better for finding me more bugs. Is that true? It seemed like maybe I don't know, right? So
it might also be better. I mean, we're at a security conference. Obviously, we want to find bugs, but it might just be better for generating test cases for regression purposes.
yes, that's true.
Cool. Thanks.
All right, let's thank the speaker again.